Okay, hi everyone. My name is Michał Zajączkowski, the Mezer. I'm here from NetGuru, and my first takeaway is that no matter how much you prepare, you always get some technical issues. So, but the guys are amazing here. So have some applause for them. I feel really privileged and honored to be here, to have the chance to share my thoughts and perspective with you. Especially that my presentation doesn't have a single Ruby line of code, and in fact, it doesn't even have code at all in itself. It's language agnostic. And gathering all these thoughts was very useful to me, and I hope that at least some of you wonderful people will find at least some useful or fresh bits in it. Let's see. And before I start, I would like to give special thanks to Michał Bronikowski here, who contacted me to give the speech. So I wouldn't be here without him. Exactly once. How to ensure systems do what we want and take care of themselves. Sounds bold, right? Stability heaven. It is. In fact, I would really like to know your experiences, but in my career as a backend engineer, more often than I would like to, I've found myself or my colleagues operating production and hotfixing production, manipulating production data, ensuring everything goes smoothly through. It's bad for many reasons, and I think these issues can actually be avoided by design, at least some of them, because what I often see people struggle with is not respecting or not providing certain processing guarantees. And of course, bugs have many issues. I won't give you any silver bullets, but I hope to give you a bag of hints and I hope a useful perspective to think about systems that will bring you forward to this goal. So let's start with a broad view. Any systems we build are made from many components, and these components process data, and they communicate with each other. And here right away comes my first advice. When you connect these components, use this recipe. So it's a kind of simple abstract pattern that will help you design and code components that take care of themselves. And we have various backgrounds, so as these elements may sound a bit vague to some of you, let's drill down into details. And I won't be saying anything new. It's like coming from wiser people, from many experiences. And for the sake of simplicity, I will use an abstraction of message passing. Message passing? Passed. Okay, so we have various actors. They send or receive messages. They also process data in between. And a very important thing is that failures can happen at any time. Anything can break. That's the most true thing in this world, and very important to remember. And this message passing is can actually be applied to basically anything. So we had great talks before about many things. We had Sidekick, right? So queuing jobs, dequeuing jobs, that's message passing. We had event sourcing. So many times I was so inspired by previous talkers. So events, passing events. This is also message passing. So to move forward, we need a few more terms. And we have 3 terms worth to remember. They are modes of execution. You can see processing guarantees, delivery semantics, very, very wise names, but let's go through them. You will see they're not too difficult. So the first one is at most once. It means that whenever I want to do something, I trigger it just once. And you have to be a bit paranoid about what you know about what you did to understand what it actually means. So if I don't know if I actually did something, but I have some trace that I might have done it, I won't try again. So in some cases, it might mean that the thing actually didn't happen, and that's the risk. The other mode of execution is at least once, and that's the other side of being paranoid. So if I don't know if something actually got finished, got executed, I will try as many times as long is needed until I'm sure about it. And here, as you may imagine, the risk is that, well, something can happen multiple times. That's also not good. And what we actually all would like to have is this exactly once. So when a sender sends a message, they mean to send it once. And the receiver, when they receive a message, and there can be various technical issues in between, they want it to be processed only once. That's like 99.99999 cases of what you actually want. And the problem is that, well, it's challenging. It's hard to achieve as an underlying mechanism without, without having something, some helpers, something leaking to your application code. Usually, to achieve this, you have to somehow take care of it. But we have the recipe, so let's see. The first thing in the recipe is at least once. So what does it mean in action? It means retry. Our message is super important, so we don't want to lose it. So we send a message, something broke. Okay, we retry, we get a confirmation that it succeeded. Great. But what if the receiver is actually in trouble? The sender doesn't know. How can the sender know, right? So, but the sender still wants the message to be delivered. And the important thing to remember is that every message you send is at least a tiny bit of resources on the other side. So whenever you send a message, the receiver has to spawn something. They reserve some CPU, they reserve some memory, whatever. And if they are already in trouble, if they're just below the out-of-memory limit, your messages may actually cause problems. And if we try hard enough, with very frequent messages, we actually can kill the receiver. And a popular solution for this is using backup strategies. So it goes like this. Instead of using constant retries, where we have this very dense retry scheme, we issue a couple of retries, maybe one, maybe two at the beginning, and we want them to be, well, at least usually, of course, we want them to be sent pretty quickly, because sometimes the problem is transient DNS problem. Or maybe it's another kind of connection problem. And many times sending a subsequent message actually solves your issue. But if the issue is not solved, then sending very many messages one after another will probably not help anymore because, well, there is some longer problem. So we still want to retry because we want our message to get delivered, but we might want to wait a little bit longer, and so we use a backoff strategy. Every time we wait a little bit longer. And popular one is called exponential backoff. That's a term you can usually meet out there if you get to see some backoff strategy. So highly recommend it. And that's not the only caveat. Let's move to the next one. With enough traffic and with enough errors, we get a situation like this, that every time something breaks, we get errors produced, right? And whenever our errors are produced, we have this error monitoring tool. I don't know what you use, maybe Rollbar, maybe Sentry or whatever. And this tool produces some warnings for the team, right? So the things go wrong, your teams go to these exceptions, they have to examine it. It takes developer cycles. So your team is busy with them. And if there is enough traffic, you get so lot of job to do just with these exceptions that you could maybe even hire one developer to go through them and fix them. And it turns out that many times there's nothing to fix, actually, because we get different kind of errors. There are these expected ones and there are unexpected ones. Now, let's park here for a minute because it's, I think, very useful to understand it, that these can even be the very same thing. So let's imagine a third party. We integrate with a new third party. And they may not have the best documentation, so you have some information in there, but there is maybe not enough information about exceptions. So something goes wrong, and how do you know how do you handle it? What's like the body of the error response? So maybe you experiment, right? You have your ways, but then in production, things break. And in such case, I imagine you might want to know about every single error because you're in this exploration phase. But then time passes by, your third party is more and more known to your team. And then these exceptions, which were previously unknown, now you know how to handle them. So there is not a big sense in still treating them as unexpected. Well, they do happen, so what? There is nothing to fix. So why do you have them in your error reporting? And my advice here is don't report issues that are expected. Only do this for the unexpected ones. And I imagine maybe some of you would ask at this point, wait, why do we ignore exceptions? Well, exception is like when things go wrong, and what if this whole third party is down? If we ignore exception, how do we know about it being down if we don't react on exceptions? And in some cases, you might be right, but it's worth to think about what triggers you to act on them. Is it like a single exception? Or is it, for example, a lot of exception? But what means a lot? Maybe some percentage. Maybe you can think of some threshold, which means things are going wrong. And to be able to capture this tendency, you use metrics. You have to collect some metrics about your traffic, and then based on these metrics, you implement alarms. So my advice here is don't kill your team and react only on the unexpected ones. So in the topic of retries, I would like to talk about one more thing. and it's when to actually finish retrying. And I would suggest to think about the sender. Who is the actor that engages in the communication? Is it me? Or is it some computer? Is it some machine, some inner part of the system that engages? Because I'm kind of impatient, so if I engage in the communication after 5 or 15 seconds, I'm already so bored and annoyed that if you don't give me an answer, I will just smash my phone and don't use your app. So for if it's a human, user experience is much more important and giving the feedback to the user than this long retry scheme. Because the user has all the manual power to do manual retries as well. So we should take this into account. And on the other hand, sometimes not retrying at all may also be not a good user experience. If we have flaky internet connection, if we don't give anything to the user, they will get errors like every single action you execute, and then it's also not the best, but we should keep it to the minimum, like 1, 2, maybe 5. It's something you should think about. On the other hand, if you connect some machines together, some components, they are very patient. They don't care. And you might care not to care about them. So it's good to think of how much time would you like them to repeat. And the answer is usually days or weeks. So that when you go to vacation and things maybe don't go wrong, but the system somehow works and you come back, you apply the fix, right? And you deploy it to production, and then your system self-heals. That's pretty much the idea. Or maybe you don't go to vacation, but it's weekend, and or you're already after work, whatever. Applying fixes takes time. So it's good to cover for various kinds of outages. So to recap this part, in a nutshell, I suggest to use retries, but don't kill your dependencies. Use a backup strategy. Also, don't kill your team. So use metrics and alarms for the expected parts. And decide when to stop based on the actors involved. So, of course, there are more things related to retrying. If your problem is more complicated, you should also think about timeouts. And there are more complex patterns you can use. It's easy to find some information about them. So maybe that's inspiration to some of you. And there are also things like fail fast, circuit breaker, back pressure, rate limiting. Maybe this will solve your use case. So that was the first part of the recipe, and the other part is idempotence. Hard word, right? Let's maybe demystify it and understand what it is, if you don't know yet. I would suggest to think about water. If I have a glass of water or this container of water, you may ask if this water is boiled. Well, if I don't know, I can boil it, right? But if it was boiled, if I boil it, it's still boiled. So boiling is idempotent. If I boil water, it becomes boiled. That's pretty much it. And for this part, I will use an abstraction of HTTP protocol because I assume that it's known to most of us or all of us. And I hope it's simple. And to implement idempotence, there are actually many things to do. And today I will concentrate only on the protocol part of it. And there are more things to mention, but it's too long for just one presentation. So I will just show you some. And to understand what's in it about the protocol, we need to exercise some protocol thinking. And by protocol thinking, I mean application protocol, because that's the protocols that we build. Of course, there are HTTP protocol, TCP protocol, IP protocol, whatever protocol. But the ones that we care the most are the application protocols, because these are the meanings of the communication. This is what you mean when you contact components with each other. So it's you who design the protocol. So, or it's your colleagues, or it's your third party who designed the protocol. And let's maybe see what we can do in action about this. Let's warm up with this protocol thinking, because I would like people to, in general, to move on from the happy path thinking. That's far too common, at least for me. And let's warm up. What's the simplest communication pattern you can see out there in the wild? The read operations. So these could be GET requests, or these could be POST requests as well, whatever. If they read data, if they just read data, they are read operations. So it goes like this. The sender sends some message, the receiver has to receive and process the message, then they prepare some data in return, they send the data, and one thing that is still important is that the sender has to acknowledge this data. Acknowledge means maybe the sender wants to save the data on their side, or the sender may want to display the data on their side. If it doesn't happen, you know already, the sender will want to retry. So this acknowledgement is important so that the sender knows that the communication is finished. And let's exercise the protocol thinking. Let's put some failures somewhere, and let's ensure that both sides finish in some expected outcome. Whatever the outcome is to be, let both sides know what the outcome is. So let's maybe try to put failure maybe here. The message is kind of received, but it doesn't get to the sender. So we know the sender can retry, and here it's again simple. Now this time things work. The receiver processes the message, sends back the data, there is acknowledgement, great. If the processing happened in the meantime, it's good, nothing bad happens, because the receiver has only a read operation to perform, so nothing changed on the receiver side. So we have no complications, no side effects out of it. So that's solved. One retry and things work. Let's put this failure somewhere else. Where can we put it? Maybe here on the sender side. So the request was sent, but the sender crashed. Or there was some bug or some temporary issue in the acknowledgement. So what can the sender do? Well, they can still retry. And of course, it may fail second time sometimes. Maybe you have a fix applied in the meantime, and then when things are to work, with the retry, they work. And what's important for the receiver, it's still the same. So the conclusion is, read operations are idempotent. I assume this may be simple, because read operations are kind of simple. So let's move on to something more complicated, which is delete operations. But if you look at the happy case, The only difference here on the diagram is this delete, right? That's worth to remember. Happy case is always simple. Let's look what can be tricky when we actually start failing. If things fail before the processing, the sender does what the sender do, right? The sender retries, we get this delete message again, and then with the processing for the receiver, it is as if the communication never happened. So it is kind of simple because they just respond with the same thing. But if the resource was deleted the first time and the failure happened afterwards, so on the sender side somewhere or during the communication bug, the situation is quite different for the receiver, and the receiver has to recognize the situation that the resource is not there. So sometimes it's simple, but I assume you might also seen bugs like this that someone didn't took this into account. So it's important to take it into account. And then the interesting part is that the response might be quite different. So depending on your use case, you may see like a not found error, or it's gone, or whatever else. And it's important that the sender knows the protocol and they know this message. And usually what the sender wants to do is just to acknowledge, okay, it's gone, great, let's move on. Great, let's not crash, but let's move on. So the takeaway from it is that delete operations are also idempotent, but there is this gotcha that you have to know this already processed message. And there are also some small points that I would like to come back later to. But to do this, I need to go to a next type of communication. So what do you have in this HTTP spec? You have like get, you have delete, and you have put. So put messages are said to be idempotent. If you read the spec, you see, okay, put is idempotent. Well, it's kind of true, but I would argue that under certain assumptions, because if you want to use put to design your application protocol, there are some tricky parts in it. I will show you just in a minute. Let's go just quickly through this happy case. The difference is that now the sender knows the ID of the resource, but the rest is pretty much the same. The receiver, upon this message, either creates the resource or updates the resource, or if the state is the same, it's just no operation. But if something fails, well, it seems like the HTTP spec is kind of right, because wherever we put this fail, we got the same result afterwards. So what's all the fuss, right? The problem is that when you change something, when you want your other part of communication to change something on their side, you may have situations when there are more than one senders in your system. And if this happens to you, they may actually operate on the same entity. They may operate on different ones, but if they do operate on the same entity, you get race conditions. Let's maybe put it on the diagram. And now it's much more complicated. Sorry for this, but it's impossible to draw anything smaller. So one important thing about this is that how a sender knows what state to put on the other side. Well, the truth is that before any update request, there is usually some read operation. So how do I know what I want to save on the other side if I don't know what is there? So most of the time, there is some get operation, and the decision about the operation usually comes somewhere here, and it's based on that state. So if there are two parties who make a decision at the same time, or roughly at the same time, and they try to communicate about changing the state at the same time, we get race condition, and this particular race condition is called lost update problem, or you can also see mid-air collision term. And there is a pretty simple solution for this particular problem that is quite easy to implement. It's optimistic locking. You can apply it to protocols, and it goes like this. We add one more special parameter, which is called version. And whenever we send some data, we attach a version to that data. So a sender gets version 1 of the resource, and then when they want to change something, they say, okay, I base my decision on this version. And if the receiver says, okay, that's the current version, great, you can do this. And now the version is 2. And if the other sender does the same at the same time, and they send a stale version, it's pretty easy for the receiver to say, that's not the up-to-date version. So I can tell you, you're making a decision on a wrong assumption. And if you do, I can give you an opportunity to change your decision. I can tell you, well, it won't work like this. And if this happens, we can just retry and it will work. But the tricky part is that we should start the whole thing from the beginning. Otherwise, we're kind of at the same point here, right? So we need to go to the beginning and we need to get a new version of the resource. So I said that there were some, I'm omitting some points when I talked about the delete operations, and let's come back to them, because this particular problem also applies to delete operations, because delete is also a change request. So let's imagine a situation when one party wants to make an update on the resource and the other is kind of about to delete it. So they get the state, they see 100, no, this cannot be, I will delete it. But the receiver side says, but your assumption is wrong. So the other party can retry, and now maybe the decision will be different, because maybe this update actually changes the game. So the takeaway from this is that when you design an application protocol, you should recognize situations when there is concurrent access to the same resources, but concurrent access to the change actions, change endpoints. And whenever you see such situations, you can apply optimistic locking. Optimistic is cool because it's optimistic, of course, but it's also cool because it can be really easily applied to protocols, and it actually is the best solution for many communication patterns. And there is one more case that you can see, roughly one more, which are the post endpoints. I left them at the end because to me they are most important, and these are the usual culprits, and they generate the most problems because they're also most generic. So they're very often these do stuff endpoints. And post usually means create me an entity. I don't know the ID, just give me a new ID, and I want to just create these things with these data. So the receiver creates the data in the happy case and answers to the sender and gives a new ID. And as you can see, the happy case is again very simple. So what happens when there is a failure? That's a very difficult question, because what can actually the sender do? If they retry this post, as we learned so far, what is the outcome? Well, the sender doesn't know if they just do this retry, because, well, how do they know? They get no information about the state on the other side. So the resource might be already there, it might not be there. And one popular convention to solve this protocol problem is to use idempotency keys. It looks like this. The sender needs this one more special step at the beginning, and it means to either retrieve or generate a unique key, a unique token. And this token is attached to the operation, maybe a field, maybe a header, whatever, doesn't matter. And then the receiver has some different job to do. They usually implement some kind of, I don't know, index on this key so that it's easy to find. So then they drill in the storage and check, do we have a resource with this key? And if we do, then we can say it's there. And if it's not, we know it's the first time. So if it's the first time, the receiver gets to know about this message, gets to process the message, they can create it. And that's how the happy path looks. So let's see how the failures look. I have to point it at the computer. That's the trick. So the sender does this token generation. They attach it to the message, and then failure happens, but this time it's before creation. So upon a retry, the very important thing is to get the same key. Why the same? Because it's the same intent. The sender has some intent in this communication, and this token identifies the intent. If it's a different intent, if I actually want to create a second resource, the key would be different. But this time it's the same, so we make this request again, we send this message again, and now on the receiver side we see it's not there. So I create it, I answer, now it's created, and upon acknowledgement the communication is finished. But if we look at the other case, so when a sender fails or when something with the communication fails upon data retrieval, if we send the same key, now the receiver can find it and tell, okay, it's there, so now I can tell you it is there. And you can see I've written down so many options here because you can see so many options up there. And if you get to this point with your team, you will pretty often get to the conversation, what should we reply? Or you implement this, and at some point, several teams gather and they discuss, well, what should be, what in our company should we answer in these situations so that we all do the same? To me, it happens so many times, so I can tell you what I think about this. So to me, it's as long as it's consistent, it usually doesn't matter as long as it works for the use cases. And the use cases are usually that the sender usually doesn't care. The sender wants just the resource to be created. So if it wants the resource to be created, it can be something, oh, it's just created, or, well, okay, I'm not telling you that it's created, it's something different. So it means that it was there, but it's still a successful response. The advantage of this successful response is that if the sender doesn't care, they don't have to do separate handling for it. So that's this tiny, maybe advantage, but the advantage is so tiny that it usually doesn't change the stakes, and the discussions can be long. So sometimes you can see like conflict response, or it's not processable, whatever, as long as it's consistent and you clearly state that it's not, that it's actually not created, that this is this use case, it's fine. And here's a funny story. I've just told you about these idempotency keys, but you can also use put for creations, and you can also see a pattern where it's the sender who decides about the ID. And if this ID is in the space of, let's say, UUID version 4, which is a bloody long random string, then it actually works, because it's more probable that a meteor right now falls here than you get a conflict in the IDs. So it's fine. You can do this. And because it's so similar, these two cases, you actually get to sometimes see either this or that. And there may be times when you don't own this receiver part. You're not the team who implements the API. You're not in the same company, and you can't influence it. And you don't have these idempotency key. And at this point, we come back to this hard problem again, that we don't know if resource is created or not, right? And maybe you have an index endpoint, and you can use this read, check, write strategy, find or create. And you first query, what are the resources? I seek for my data, and then I decide it's there or it's not there. If it's not there, I proceed with creation. So if we have a failure before things are created, then we retry the whole thing, this whole protocol, and then we make a GET request. We see, oh, it's not there, so I create it. And this time it works. Great. But let's look at the other case. If it was created actually, then important, we repeat the whole operation again. And now we can see the data that's somehow unique enough data that the sender is able to recognize that it is there. And upon this step, it decides, I don't need to create anything. So I just acknowledge the communication is finished. And that's very nice and useful. I think pretty much everybody gets to use this pattern in some form, at least at some point. But it comes with a couple of caveats. So the first one is that just in this form, it's prone to race conditions if we have multiple senders working on the same data. If they plan to create the same entity, you will have some duplicates sooner or later. And the other one is even more tricky because it deals with consistency. So the receiver might not have a consistent workflow on their side. And if you don't own the receiver. It may happen that they trigger something during a failure that fails, but the resource creation works. And the whole workflow might not be successful, but the resource itself gets created, so you get it in the index endpoint, right? So then the sender doesn't retry the communication. And if that happens, you usually don't know it at the protocol level, because how do you know it? That information is not there. That's some internals of the other party. And you may say that's a problem of receiver. And that's usually how this conversation ends, when it goes to the upper level and you meet people and say, what is your problem? Because some other feature out there doesn't work for you. You don't get the value from like other side of that party. And that's usually how it goes, but it's still kind of problematic from the protocol side, because you can imagine another situation when you actually are on the receiver side and you would actually want that other party to repeat if they get an error. You may say, you know, guys, but if you get a 500, just shoot this other request to us. That can be some solution, but it requires consistency, or it requires idempotency key again. So we get back to this first problem. So you see, it can be problematic, but in some cases, it's the best thing you can get. So if that's all you have, just go for it. And the problem comes when you have neither this nor that. And if that's your case, well, you kind of get a problem. And you might come back to negotiation board and, well, say, you know, guys, but it's really hard for us to move from this point without this idempotency key feature. When would you be able to implement this for us? And you may actually get a response, well, yeah, we can actually do this. And that was my recent case. It worked. The other time, maybe you would like to change the API provider, because maybe if they are not responsive to your feature requests and it's really hard to work with them, then, well, maybe you can find something else that does your job. Or you just have to accept the duplicates, right? So that's pretty much it for today. Let's wrap up. Oh no, come on. How can we wrap up if real-life implementations are way more complicated than just these simple CRUD operations, right? Where is all the talk about like consistency, about side effects, about all other beasts are there which are actually difficult? That's true. It's not like all that you have to do to achieve this idempotence property. It has a couple of more things into it, and they are actually on this receiver side. I briefly touched it just a minute ago with this consistency, so that's one of the things you have to consider. But as you see, it's just not possible to put everything in just one talk. So maybe another time. But I would argue that on this protocol side of things, that's like this first thing you have to do about idempotence. That's roughly about it. That's roughly what you have to do to at least enable the parties to get their workflows right. So to wrap up now, I presented you like a bag of hints and some perspective, but actually coming back to my main thought for today, that's this recipe. If you were to remember one thing from this presentation, I would be very happy if you remember this. because, well, it's not a silver bullet. So what does it actually give you? Well, it enables the system to resume communication when problems happen and take care of the workflows that you have in there, and eventually you enable the system to self-heal when the problem is gone. So you will have much less this babysitting with your systems if you use it. Thank you.
Thank you very much. It was quite helpful and viewable on these schemas. Could you go back and show this schema where we had this create and this independency key?
Mm-hmm. Sure. Let me just find the slide. Mm-hmm. This one?
Yes, exactly. And the case when we retry it. Yeah.
When we retry it, okay. We have two slides because we have two cases.
Mm-hmm. Yeah, in this case, I want to really know when we retry, potentially if we post with some parameters that depend on some entity, right? And potentially the state of entity could change, right? Entity can be updated. When we're doing retry, we could have new parameters for this entity. And the question for me, what is more correct? If we make a retry and this source of truth has changed on the sender side, I mean this entity was updated. Yeah, it's columns. Should we directly change post data on retry and make it in up to date with this entity updated fields, or should we make two queries? One of these is post with all data and probably put with new changed kind of attributes. What do you think?
So that's already much more advanced situation because it, as far as I understand, it assumes that the state of the resource can change in the meantime. So we have some other party here, right, that can influence the state in the meantime. And again, that's a race condition. So if we have a race condition situation, we can apply again the optimistic locking. So how would it work in this case? Well, we can, for example, attach version 0 here. And if we do that, then the receiver can recognize the situation that the resource is, well, fresh, then it answers with 1, and the other side can, well, depends on what they do, but if they manage to, well, that's actually the other case, maybe then I will, it's created, right? So at this point, if an update comes and, well, I get an update, and here we have this other version already, at this point, when we get this version 0 again, we can say, well, you know what? That's no longer valid. So you are able to recognize this situation with optimistic locking. And depending on your case, you would probably discard this. Or you would say, well, that was already created or already modified, and you are able to handle this on the sender side. Usually, probably the sender was just about to create this resource. So if it was to create it and it wanted to finish its workflow at some point, they, for example, might have here some events to produce more or some side effects to fire. So they might want to continue this workflow and so they have to acknowledge it in a way that doesn't make them crash. That would be my assumption.
Thank you very much.
Yes, please.
Okay, first of all, you have a very interesting surname. I would love to know the story. But the question is, let's say you're working with a third-party API, which doesn't support idempotency keys, and you can't really use the technique you showed when you get all the entries and browse them, because that's really inefficient if there are thousands of entities. And it's, as you said, it's also prone to race conditions.
Yes.
So I'm wondering, are there any other solutions, to that problem to make sure you can create only one item in the third-party API?
So one other way is this put. I've showed you with this, if you can choose the ID, but you might also not have this one. And if not, then that's this negotiate state where you have kind of a problem. You have to somehow compensate for this. If you have to stay in this situation, for me, that's a wrong protocol. That's a protocol that doesn't save you from edge cases which are difficult to handle. And if you cannot do anything about this, well, sometimes maybe you can compensate for this. But it's difficult and costly, because you may still end up in a situation when you have to query for the state somehow. You have to somehow find the way to validate, was it successful or not. It will be painful. I would say negotiate. That would be my first go-to point. Go and say, you know what, that's not good, really not good.
So now you're really putting me on the spot to ask a good question. And it's terrible because I didn't have a really good question. I have more of a sinking feeling. And I want you to confirm or deny it. And the problem is that as soon as you have this idempotency keys and so forth, which I totally agree is what you want to do. The thing is, if you're failing on the receiver end, because you're only going to have these issues because you're failing on the receiver end. Usually the problem is that the receiver is overworked, so they need to scale out. The more they scale out, the harder it is to implement idempotency on their side, because fundamentally, the only way to implement an idempotent system from their perspective is they need a central place to, they need like a one transactor or one locking mechanism. They need some place where they can actually guarantee that atomic operation. So I have this sinking suspicion that the more you have race conditions, the more the receivers are overworked, the more they need to scale out, the less likely they are to actually allow this kind of thing. So is that your experience as well?
That's a very valid point, and that's a point actually about this CAP theorem, right? There's like consistency, availability, and partitioning. So that problem is about this partitioning, because at some point, to still be able to process data, you have to somehow divide it. You have no other way to ensure that things don't slow down. And for this specific problem, the solution is, well, kind of simple, because you can apply, it's called sharding, I think. So, for example, based on some hash function, you decide to which partition that entity goes. And you may, for example, have 50 partitions, right? But based on this hash key, which always gives you the same result, you say, oh, when this resource gets created, it goes to partition number 30. And that partition will then do this job. And because this relationship created by the hash function or another method is deterministic, you will always get the same result. So these partitions will be disjoint. They won't have the same part. So I assume that would be the solution for this particular problem. And I assume that's not the only problem you have to solve eventually. But thank you very much for the question.